Welcome everybody to Red Hat Research Days. Today we have a really interesting talk about how to prevent your Rust programs from becoming C programs, which you'll find out more details about what that really means from the speakers as we go along. I'd like to welcome Baishaki Ray, who's an associate professor from Columbia University. She has an interest in traditional and AI-driven software development, and she's also the leader of the Arise Lab at Columbia University. And that lab's goal is to build novel techniques and tools to improve software robustness and developer productivity, which is certainly of great interest to us at Red Hat and in Red Hat Research. So welcome, Baishaki.
Thanks.
I'd also like to welcome Mulhern, who is a Red Hat developer, very experienced in Rust and a principal software engineer. Mulhern has been associated with the research group for a while now, and we very much appreciate her suggestions and input and projects. She is a part of the RHEL ST platform storage project and has been contributing to Red Hat in that capacity for quite a while. Vikram Nitin is a PhD student at Columbia, and he is the person who has been carrying on a lot of the preliminary research on this project, along with us in a collaboration, and it's been very interesting. Thank you for being here, Vikram. And last of all, Sanjay Arora, who will be our conversation leader from Red Hat today, both asking questions and encouraging, hopefully, folks who are attending to join us with the video and audio join options here in Hopin. Sanjay is a senior principal software engineer who's interested in AI and machine learning and is part of the AI platform enablement and research teams and is especially interested in all things system engineering and how to investigate and improve system engineering, especially in cloud systems. So welcome, Sanjay, and I will hand it over to you now. I hope you all enjoy this Research Days event.
Yeah, so before we start, just a couple of pointers about questions. So on the top right of the screen, you should see 3 tabs, and one of them says session. And there's a chat in the sessions where I see there are several people. So you could type your questions there, and we'll interrupt the speakers every now and then to ask them the questions. The other option, of course, is for you to hit the join audio and video button on the top right too, and join us on the virtual stage. So please don't be shy. Please join us here, ask questions. This is very informal, and we want to make sure everyone is engaged. So with that, I'll hand it over to Mulhern, who will set up the context for us before we hear from Vikram.
Okay, thanks, Sanjay. All right, so I'm going to begin this talk, and first what I'm going to say is who I think might actually get some benefit from this talk. And I think an audience of people who just are generally interested in Rust and want to hear a bit more about it and about how it works, what kind of language it is, could get something out of this. Another group of people would be people who do program in Rust already, but who are wondering where are all the static analysis tools that they find in other languages. And I'll just mention that there's a really good static analysis tool for Rust. It's called the compiler. It does a lot of great static analysis. But where are the other ones? They might be wondering. I've been wondering that for a few years, and we'll talk a little bit about that. Then there might be people who write unsafe code in Rust and are feeling a little bit cautious and are wondering if they're doing it quite right, or alternatively are wondering if there's something more that they can get from the Rust ecosystem that'll help them be sure that they're writing it correctly. And finally, you might be a person who's been programming in pure Rust very happily and then have somehow run into a bug that was eventually traced to unsafety somewhere in your program. And you might be wondering exactly how that happened, given all the information and boosterism about how Rust is safe, and that can't happen. And so those are all perfectly valid reasons, I think, to be attending this talk. Okay, so who am I? Please, if you want to call me my name, call me Mohern. That's what I always go by. As it happens, I do have a PhD in computer science, but as was explained, I'm not primarily a computer scientist or researcher anymore. I lead the Stratus team, which develops its principal component, the Stratus D daemon, in Rust, and I've been doing that for a number of years. So while I'm certainly interested in and somewhat versed in research issues, my principal contribution was to sort of get the project going. Okay. And as Sanjay said, speak right up if you've got a question, and I'll be happy to field it, talk about whatever interests you. And then also I'll just be presenting slightly the background, and then I'll yield the floor to Vikram. Okay, so after a couple of years of working on the Stratus project, I was just as excited about Rust as I had been when I first started learning it. And I was looking for a project that would demonstrate how great Rust is, somehow, a research project that would prove the wonderfulness of Rust, which I felt so strongly. But honestly, there are some obstacles or difficulties about Rust, which I'm going to be really quite clear about here. One of the things that's very, very important to understand is that Rust is actually pretty hard to learn. When I started learning Rust, I had a background of having programmed somewhat seriously in at least 5 languages, somehow less than 10. And I had a good background with the sort of static type systems, but I still found Rust to be difficult. I plowed through the syntax, and then I struggled with the strictures and restrictions imposed on me by the borrow checker, and was grumpy for about a month until I settled down to being pretty consistently able to write Rust programs. And the point also is that even once you've settled down and are writing Rust fluently, it still is harder than some other languages. You have to go back and fix up things a lot to make sure that they do obey the borrow checker, etc. And then refactoring, once you've got a nice big program, you want to make a change, turns out that that's painful, can be really painful. Sometimes the special pain comes when you've induced a huge number of type errors and you fix them, and you're fixing that last type error and you're really happy. And once you fix that, a whole lot of borrow checkers errors are suddenly spewed back at you that you just didn't know were coming. And this can happen a lot if you're a naive programmer. And there are other Rust people on here, I'm quite sure, and you are probably thinking of other ways in which programming in Rust is real work. Okay, so with all that said, why do it? Why develop your project in Rust instead of some other language? And actually, it's great, I still believe this, to develop in Rust. There's so many good things about it. And I'll also admit, just as an aside, that some of them are not really to do with the language, but to do with the ecosystem that was built at the same time and with great forethought, the packaging tools, et cetera, et cetera. So it's all really, really good and very smooth to work with. But right now, I'm just going to discuss language-related things. So one way to sort of get at why Rust is to compare the experience with what it would be like to develop in other languages. And that's really what I've been talking about all along. So one way to do this is to compare it with the experience of developing Python. And this, you're not supposed to read this, it's just, this is sort of encapsulates the experience of developing in Python, which I'll admit is a language I also like. But the problem is that every single method call and attribute access has an implied has an implicit assertion, the assertion being this one is going to work. And it's entirely up to the programmer to ensure that it does work and that you don't see a traceback like this. And the problem with these tracebacks are not so much that they happen, but that the object that causes the traceback can have been produced very far away, both statically and in time in the code. It finally reaches a point where an attribute access or a method call is made, and it's only there where it finally crashes. And so these bugs can actually linger in large Python programs for years with everybody wondering, where does that object come from? And so I argue that these are boring. They're not necessarily interesting logical bugs, but they just happen. They're the bugs you encounter when you program in Python. And then we have C instead. And so then the question is, well, why not develop in C? Lots of people do. But C has this other problem, which is that rather than having calls fail on objects, what you have is lots of memory problems. So basically the bread and butter, as we all know, of C programming is to mess around with pointers. And the pointers do sort of end up wandering about in memory and accessing memory that they aren't expected to access. And while I'm showing you the good classic seg fault, that's kind of an easy one because at least it's very visible. The really more troublesome errors in C are the ones where the program is accessing memory, unexpected memory that maybe belongs to some other part of the code. And it does that for a while before this problem is visible. And so then you have the same problem you have with Python, that you're not sure where the original origin of the mistake was. You only see the later effects, and those can be very hard to find as well. Okay. And all these things don't happen in Rust. And that's great. And that's one wonderful reason to program in Rust, because Rust presents two really good things. It has the flexible and expressive type system, which I was already familiar with when I started working with Rust, although there are definitely subtleties in Rust, which one could talk about, but that thing is already there. And so that prevents those stack traces, those Python stack traces that I was showing you. And then it has also this borrow checker, which presents a good class of those C-style bugs that I was just complaining about. Of course, as I mentioned before, it can cause all sorts of annoyance to the developer, but it's very powerful and helpful too. And so I claim, and this was my claim all along, that developing these software projects in Rust is just more fun. It's a better experience. So in the end, when we wanted to compare things, we ended up ignoring Python entirely and focusing on C, because Rust has an interesting relationship with C. So first, Rust and C are sort of in the same domain. I've used Rust programs to generate, static website generators. So it's not as if Rust is restricted to system stuff, but it's good at system stuff. And so they frequently can be thought of together. And then there's a sort of way, and I put this advisedly in quotes, in which Rust includes C. And not literally, but in an interesting sort of way. And so now here I have, again, a fake program, which you don't have to look at very closely, but it shows a sort of pattern where you have these unsafe blocks in a function, and within them you have code that is C-alike. It doesn't look like C, but it has those actions that C also allows, which I was just condemning and saying are the source of all your trouble when you go ahead and program in C. So actually you have Rust, but Rust allows you to write chunks of code that are like C. Okay, so why would you do this? I was just saying C, there's all this sorrow and pain. Rust, it's so great. It prevents all that sorrow and pain. Why would you do that? And it turns out that because Rust is in that space, there are lots of great reasons for you to want to do that. One is, and this is important for Stratus D, so I'm sort of familiar with this, is that if you're wrapping C libraries, the C libraries themselves have that unsafety. The typical way of doing it is to make an unsafe lower layer and then wrap it in another layer. And then you may find that the borrow checker is, or even the type checker that can happen, is too restrictive. And there's some optimization. This often seems to arise in data structures where you don't want to be restricted by to be writing pure Rust. You want to manipulate those pointers and so forth. And so I think other Rust programmers will be thinking, I have my own reasons too for doing that kind of thing. And I'm sure there are many more, but those are always the ones that immediately occur to me. Okay, and so now this is just a statement about how this unsafe stuff works. And it's not about the mechanism of unsafety, but simply what the compiler decides is unsafe. So there are some things that the compiler knows, that's the base case, are unsafe by definition. And then a programmer can declare functions and blocks unsafe if they feel like it for whatever reason. But then if a function contains an unsafe portion, then the compiler requires that it itself be declared unsafe unless it wraps these unsafe bits in the unsafe blocks that I showed you earlier. And so the question is, when you're writing Rust code, but you're writing, say, a library, what do you as a programmer want to try to do? And I'd say you want to minimize the static size of your unsafe code. Less here is more, just because the more unsafe code you have, the more thinking you have to do about it, more or less as if it is a C program. And also, you have a sort of contract with the users of your library. And that is that if you don't label the code unsafe, then it should behave as if it was pure Rust to users of your library. And of course, you can err in doing this. You can allow that unsafety to actually escape and be present in functions that are not labeled unsafe. And then the user of your library will experience the result of that. So you might say, like, maybe I'm making a big deal out of nothing. So I did a couple very basic things. Well, I did one very basic thing is I wondered about the code that Stratus D depends on transitively or intransitively. So not transitively or directly. It was easy enough to find that. And so I just did a search for the word unsafe, and I found almost 6,000 occurrences of those. So it's clear that in the code that Stratus D, which is storage software and very only just in user space, it's clear that that code that it depends on, the libraries on which it depends, find many reasons to use unsafe, that keyword. And then I also will mention that Rust, this is one part of the wonderful Rust ecosystem, keeps a database of vulnerabilities. And if you just scan them, you'll notice that a bunch of them are actually memory related and result from C-like behaviors. They're not all interesting bugs, although some are. Okay, so next up, I'm going to just yield the floor to Vikram, and I'd like to know, are there any questions before I'm done? And I'll stop here.
I don't see any questions in the chat, but if anyone has questions, please put them in the chat or please join us on the stage. And if not, we'll Yeah, Vikram, you can go ahead and share.
Okay, let me unshare.
Okay.
I believe I have unshared.
All right. So, give me 1 second. Do you all see this? Is it full screen too?
That's perfect.
Okay,
Yes.
great. So Malhan was talking about how we have this concept of unsafe code in Rust and how that introduces potential vulnerabilities in our program. And what I'd like to do now is talk a little more about what are some types of these vulnerabilities, right? So more concretely, how do they arise and what are their different types? And then later on in the presentation, we look at how we can prevent them and prevent some classes of these vulnerabilities. So, as Malhern said, in when she looked at Stratisty, she found like a few thousand uses of the word unsafe, right? And the percentage of packages using unsafe has not decreased significantly with time. As you can see, this line is more or less flat, although maybe sloping down very slightly. So, what this means is that if you rely on a package using unsafe, you are essentially relying on the fact that whoever has implemented this unsafe package has done it in a way that encapsulates that unsafety, that makes sure that the unsafety is not exposed. And that is a tricky assumption because it can transitively break the workflow down the line too. So if I rely on a package that uses unsafe, and then someone relies on me, and then someone relies on me, we are all depending on the um, safety of that one function, one unsafe package upstream to have implemented its unsafety correctly, right? So it's very crucial to ensure that unsafe code does not have memory safety bugs and other types of vulnerabilities, right? So that's sort of the motivation where we're coming from. The fact that such a large proportion of packages use unsafe, and we want to ensure that the ecosystem as a whole is safe. And there is something called the Rust Security Advisory Database. So this tracks um, security advisories and vulnerabilities that have been filed against Rust packages. The technical name is crates. Okay, so the number of advisories filed per year has been steadily growing. We had one in 2015, six in 2016, and all the way in 2021 we had 141 advisories. So this means that, like, naturally, as the number of packages has been increasing, as the number of crates has been increasing, we do report more unsafety bugs, and it becomes all the more important for us to sort of weed these out and become better at detecting them, both on the detection front and on the sort of resolution front. We need to become better at both of these aspects, right? So we did a sort of empirical study. We sampled like 50 RustSec advisories, and here are some of the types we found, right? So you have one big class is memory safety errors, and these are perhaps, um, as we'll see shortly, one of the strongest guarantees that Rust provides is memory safety. And these sort of go very fundamentally against the ethos of Rust. So these are sort of an important class of bugs. There are various types. So some of these are, for example, we'll look at some of these features in a while, but a lot of them have to do with like incorrect checks or the programmer being lazy while implementing unsafe code. You've got to be very rigorous in what you do and very careful in what you do. So some other classes are things to do with thread safety, things to do with integer overflow, and there's a whole host of these vulnerabilities, right? And you might be wondering, with the number of growing advisories and the number of packages using unsafe and the number of different vulnerabilities different types of vulnerabilities that we found, you might wonder, why use Rust, right? Well, the answer is that the pure Rust language without unsafe provides very strong memory safety guarantees. And further, even with unsafe, the types of bugs you find in Rust are still, quote unquote, more interesting than bugs you would find in other languages. So something that would perhaps just be a bug in another language is perhaps serious enough to be filed as a CVE, vulnerability in Rust, right? So you're automatically operating at a sort of higher level of abstraction. You're operating at the level where you can sort of eliminate your boring kinds of bugs and now focus on things that are genuinely like interesting bugs. Um, I'll qualify that in a bit. We'll go through the presentation and see some types of bugs that arise, and we'll through that maybe um, get a finer perspective on what we mean by the statement. So I'm going to pause here and ask if there are any questions up till this point. So, I'm not looking at the chat, so if there are any questions.
Vikram, you're good.
Okay.
You can carry on.
Okay, so now we'll take a. So we've looked at the various kinds of vulnerabilities, and I discussed how a lot of them exploit certain features of Rust. What are these features of Rust? We're going to look at them one by one and understand what makes Rust such a unique and such a powerful language. So let's start with perhaps the most central and unique feature of Rust. It's called ownership. So this is something which, to my knowledge, is not a feature of any other programming language, or maybe any mainstream programming language. Ownership, right? The concept that every allocated heap memory value is owned by a variable, right? So that essentially means that you associate a certain variable in main memory with every heap value. There's a one-to-one correspondence, and only one owner at a time. Once the variable attached to it goes out of scope, the heap memory is freed or dropped. Okay, so you cannot have a situation where you have like a heap memory which has been which has nothing pointing to it, right? Like in C, you could have a pointer where you allocate some memory and then the pointer goes out of scope, right? So the memory is now left behind. There's nothing pointing to it anymore. It's like a orphaned block in memory. So of course, there are things like garbage collection and so on, but that is sort of like a patchwork kind of solution, right? You sort of do that on top of the language, and it's sort of clumsy. It's not guaranteed to work, and it has lots of limitations associated with. Of course, static analysis is limiting, so it's sometimes difficult to tell when to do garbage collection and so on, right? And of course, C doesn't even have garbage collection, so that's another inherently doesn't have garbage collection. So with all this, Rust imposes a very strong guarantee that if you have a memory location, you have something pointing to it, and once that thing stops pointing to it, the thing goes out of memory. Okay, and we're going to look at some examples to see how that actually happens in practice.
Vikram, so can I interrupt you with one question?
No problem.
So there's a question from Ari, which is, does Rust absolutely need unsafe to be functional? Does it actually need that unsafe feature to be functional?
So,
or is pure Rust not practical?
Yeah, there are some. So the problem with static analysis, this is essentially the compiler doing its own version of static analysis and saying that you cannot write code like this, right? And we're going to look at some cases where it actually over approximates. So static analysis is always either an over approximation or an under approximation, right? You cannot have like perfectly precise analysis with static analysis. So what that means is that you can have cases where valid programs that do nothing to compromise memory safety, are still flagged as not allowed by the Rust compiler, will not compile, right? And that is a case where we want that extra flexibility. We want to be able to say that, look, I know what I'm doing. So I know that this program is memory safe. It's just that according to the semantics of this language, I'm not able to compile this. So Unsafe sort of gives us a way around that. It lets us still write that code and go ahead with writing that code in situations where it says, okay, I trust that you know what you're doing. Provided that you know that, just go ahead and do what you think is right. So that's the guarantee that Unsafe gives us. Okay, so moving on, let's look at some examples of how this works in practice, this ownership concept, right? So just to recall again, heap memory is owned by the variable that points to it and is dropped when the owning variable goes out of scope. So here is a heap variable, a string we allocate on the heap using this string constructor, string from hello. And this is the variable that points at it. So a variable s points at this location in memory. Now, as soon as this goes out of scope, the memory is dropped. So the statically defined scope of this variable s is this, right? And as soon as that scope ends, the location that it's pointing to is also dropped. It's that simple. And then here we have a very interesting concept, right? So now you may ask, what if we sort of duplicate this ownership? What if we try to sort of transfer ownership from S to some S2? So we allocate S1 equals that memory location, and then we try to transfer that to some variable S2. And what actually happens here is that S1 gets invalidated now. S1 no longer points to hello. And this code will not compile. Rust only tracks one at a time. If you ask it to track two variables, both pointing to the same thing, it will not compile. Because, as I said, there's only one owner for every heap location. Right? So, however, if it's a stack variable, like a primitive type, there are some primitive types in Rust, like integers. If it was a primitive type, there would be no problem. X equals 5 and y equals x. X would still be valid. So this means that heap variables are like a class, it's different class of variables, right? They are different in some very fundamental way to stack variables. And so this is a simple example of ownership. Now we're going to look at more. In the case of functions, right? So okay, again, if I should probably again just check that there's no questions here, because this is sort of a new concept. This is slightly non-intuitive.
So there are no questions directly related to this, Vikram, although there's a nice discussion going on about the use of unsafe.
Okay,
But yeah, you can go ahead.
good. Okay. So the other case is now ownership and functions, right? What if we pass a value into a function? And sure enough, what happens is that the function now takes ownership of that s. So now let's say I take this s and move it into the function as an argument, right? I pass it as an argument here. Now this s inside the function now has ownership of that heap object. This loses ownership. Okay, so again, it's like a very strong guarantee. We know exactly where this variable is. We know exactly which variable owns this memory location. We can transfer ownership or we can retain ownership. There's no in between. Two variables cannot have ownership at the same time of the same heap location. Okay, so s and s here are actually different variables, and the original s loses its ownership. However, again, in the case of a stack variable like 5 over here, there is no problem. There is you have the variable passed into the function, and you're still able to retain access to it, right? So again, proving the point that heap and stack variables are different in this regard. I'm going slow just because this is sort of a this was new to me. This was sort of slightly non-intuitive, and it took me a little while to understand when I first started working with Rust. So if there are any questions, please speak up. Like this is, I understand if this is slightly confusing.
Vikram, there was about your previous slide.
Sorry, Sanjay, your voice is breaking a bit. I didn't quite hear you there. Hello?
Wait, what just happened? Did we lose connectivity briefly?
So I think, okay, Sanjay was saying something, but
Yeah, I think Sanjay had problem with his connectivity. The rest of you are fine. I think.
Yeah, I think we lost Sanjay for the moment.
I think he will be rejoining probably.
Yes.
there is an interesting point about move versus copy versus instead of heap versus stack. Yes, that is the technically correct terminology. That's true. In one case, we're moving the value into the function, and in the other case, we're copying. That's true.
Sanjay is back. Sanjay, you were
Yeah.
saying something?
Yeah, I don't know. So I was kicked out, but the question was, let me look at it again. So Vikram, the question was, I think 2 slides, or maybe this one, where when you say dropped, do you mean the memory is freed?
Yeah, exactly.
Yeah. And I think that was it.
So yeah, there was a point about how move versus copy is what's happening here. So heap variables are moved into the function. The stack variables are copied. So yeah, that is one distinction. But essentially, in practice, what that boils down to is that if uh, I can duplicate ownership of a stack variable like this, and I cannot duplicate ownership of a heap variable like this. As in, the object itself is duplicated in case of the stack, right? So that's what it boils down to in practice. So now what is the way around this, right? Suppose I want to pass something into the function but still retain possession of it. One way to, I mean, if I want to use it afterwards, I could perhaps return it from the function. I could say do something with s and then return s, and then s equals foo of s, and then let s equals foo of s, and then continue on, right? So that's one possible way to do it. The other possible way is something called borrowing, and borrowing uses the this kind of syntax, the syntax of references. So it's quite simply indicated with the ampersand symbol, indicating that the value is not being moved into the function, but being borrowed by the function. So we can, yeah, it's analogous to maybe references in C, pass by value and pass by reference. So this is essentially passing it by reference, if you can think of it that way. We take the value s, pass a reference to it into the function, do something with that reference. Foo can now manipulate this s, and sorry, Foo can now use this s, and then we can continue using s as normal in the main body, right? However, this does not permit us to manipulate the object we're passing. Okay, so this does not yet have ownership of this, and that's reflected in the fact that it cannot simply modify this. It owns a reference to the object, but it cannot modify that reference. Okay. So just to recap again, the different cases are when we pass it in, we lose access here, right? But then when we pass in a reference, we still retain access but cannot modify it. Okay, that's where we stand now. Now the next concept we need to look at is something called mutable references, right? Mutable references are quite simply a way to pass it by borrowing and still retain access. And also the function that borrows it can still modify the value. Right now, I know that sort of goes against what we've been saying. Like, okay, we need to know where it's being modified from. We cannot have multiple things pointing to the same. We cannot, but there is still a sort of very strong guarantee that Rust gives us. It gives us the guarantee that you can only borrow it mutably once. So if I borrow a string mutably once here, I cannot again borrow it in a mutable fashion. Okay, so I have a variable r1 that's borrowed s in a mutable fashion. I cannot have another variable r2 that again borrows it mutably. And further, I cannot have an r3 that borrows it mutably. What I'm not saying in all these cases is that we need to use r1, r2, r3 after this. Otherwise, it'll treat these as separate static scopes. It'll say that, okay, it's no longer active. But let's say I try to use r1 over here or r2 over here. That would be a problem, because it would say that, look, in this scope, you have R1 active and R2 active. Both cannot be active at the same time. You cannot have two mutable references to the same location. Similarly, you cannot mix mutable and immutable references. That is, you cannot have a R3 and an R1 in the same scope.
So Vikram, there's a question from by Ari about this. He's asking if you can re-borrow R1 mutably.
Like R2?
Yeah, R2 is basically borrowing R1 in a mutable fashion. Like you have a chain. Is that possible?
Oh, in a chain fashion. Yeah,
Yeah,
that should
that
be
should be okay, right?
that should be okay. Yeah. Um, so, but then that wouldn't modify the value in S. That would only modify the value of R1, right?
Yeah.
You could change R1 now to point to something else. You wouldn't be able to change S through R1, R2.
Yeah, that makes sense.
So that that's where we've set up now. So we have this system of ownership where if you pass something, if you move something, you lose access to it. If you borrow something, you still retain access, but you can't modify. If you borrow something mutably, you retain access and you can modify, but you can only have one at a time. So that's the entire setup of the system of borrowing and copying and Rust and moving. Yeah, I'm going to move on at this point. This is sort of set up the framework for what we're going to discuss after this. Now that we have some idea of the way borrowing ownership works in Rust. Okay, so if there are no further questions, I'll move on to the next feature of Rust.
Yes, please do.
Okay, so we have this like great system. So what's the catch, right? It seems as though if we just stay within the system, we know exactly where everything is being accessed from. We know that when something goes out of scope, the owner goes out of scope, the value will be dropped. So it seems like we have a great system, right? Memory management seems like a breeze if you just stay within this framework. So what's the catch? The catch is that we may need a finer level of control sometimes. So look at this simple case. This is an array in Rust. I know we haven't introduced this syntax yet, but this defines an array of length 6, right? And I want to say my first half is this, and my second half is this, and I want mutable references to both of these. I want to say do something with my first half of the array, do something with the second half of the array, and do them separately, but have mutable references, right? Rust will not allow this. It will say it cannot have two mutable references to the same slice. And that's not the compiler's fault, right? The problem is that static analysis is inherently an overcompensation. So it doesn't see that like it's the first half of the array and the second half of the array. It instead just sees it as two mutable references to the same array. Right? And we know that that's like not a problem. We know that they'll never intersect. There's no way that modifying one can result in the other one also being modified. But Rust says no, right? Because it doesn't understand that we know what we're doing. So the solution to this is something called raw pointers. Okay, so by the way, I should comment that this perhaps answers the question from earlier about why unsafe code is even necessary in the first place, right? If we just operate exclusively within safe code, we may end up in scenarios where we want to do things like this, but we're just unable to because Rust won't let us, right? So that answers the question about why we need unsafe in the first place. So raw pointers are the answer to this solution. Raw pointers don't have the same guarantees that normal references do. So everything we discussed so far, the system of ownership, automatic cleanup, two mutable raw pointers, none of that applies. Everything goes out of the window, right? You can treat them in the same way as you treat like a pointer in C. It has all the same pitfalls and all the same flexibility that a pointer in C has. So Rust is basically saying, okay, I trust you know what you're doing, just handle the guarantees yourself. Okay, so that's exactly what happens here. You have this number 5, and I'm borrowing it. Initially, I'm borrowing it normally. Later, I'm borrowing it using a raw pointer. And there are two types of raw pointers: the immutable one and the mutable one. Okay, so that's this that parallels the system of mutable and immutable references. And now this so far hasn't used any unsafe code. So you've created these raw pointers and we haven't used any unsafe code. So You may ask, how is this okay, right? Like, how is Rust okay with us just creating raw pointers without explicitly marking it as unsafe? The answer is that to dereference raw pointers, you need unsafe code. You cannot do like star R1 if you don't have unsafe code around it. So that is one of the superpowers that unsafe code gives you, the ability to dereference raw pointers. I think there are 5 superpowers, and this is like the first one of them. The others we're not going to look at in the course of this presentation, but know that there are like a few others that it gives you. This is perhaps the most sort of crucial and most the one that sort of breaks the most rules in some sense. All these rules are sort of they take a temporary hiatus when you encapsulate something with unsafe, because what that essentially means is that the pointers inside don't obey any of the guarantees. The raw pointers inside don't obey any of the guarantees that normal references in Rust do, right? So that's what's going on here. We're having a system where we can suspend all these guarantees just by enclosing the code in unsafe and dereferencing these raw pointers. Okay.
And Vikram, related to that, there's one more question by Wander. Can you do pointer arithmetic in unsafe blocks?
Sorry, pointer arithmetic would be like R1 plus R2.
I think that's what Wander means.
Yeah, I suppose.
Or like adding, like,
R plus
shifting,
1.
yeah, R plus 1, R plus 4, shifting by n
Shifting
bytes.
by, yeah, sure. I think that should be allowed. Yeah, it is allowed as far as I know. I know that you can create like raw pointers from raw memory addresses. Like I can define a memory address like OX554 and then define a raw pointer to that location, and then you can
add a byte or something.
Yeah, you can probably add a OX01 or something of that sort to a raw pointer. I haven't tested it myself, but my hypothesis is that you can.
Okay. Thank you.
Yeah, as you can imagine, this is quite dangerous. We need to sort of be very careful while writing unsafe code to ensure that things downstream still see this as safe code. And what I concretely mean by that is we can use unsafe in 2 ways. One way is to sort of encapsulate the unsafety. That is, we put unsafe code inside a function, and we don't let anyone calling the function know that there's unsafe code inside. So as in, anyone calling this function foo should be able to call it as though it's a safe function. They should not have to worry about the fact that there's unsafe code inside, or maybe worry about the kinds of inputs that they can pass to this function. They should not have to restrict their use of the function in any way. So for all intents and purposes, this function foo should now behave as though it's a safe function. It should not like give errors for valid inputs, or yeah, it should behave just according to whatever the Rust type system guarantees us. Any valid integer, for example, should be an input, can be an input to this, and it should not crash or otherwise signal any kinds of errors. That essentially is what this tells us. If we omit a label unsafe on this function. Now, the other way is to expose the unsafety and actually label it as unsafe. Then everything inside the function now becomes unsafe. You don't need this unsafe block anymore to dereference the raw pointer. And this in turn means that anyone who's calling this function, A, can only do so inside an unsafe block, and B, must be careful about what types of inputs they pass to the function. Okay, is that clear, the difference between these two types? One, this function behaves like a safe function and provides no hints to outside people who are calling this function that there is actually unsafe code inside. And the second case is where you explicitly mark it as unsafe and expose the fact that it's unsafe to anyone who's calling it. So that means, again, 2 things. One, you need to call it within an unsafe block, and B, you need to be careful about what kinds of inputs you're passing to the function, because not all inputs are acceptable, basically. Is that clear? Is the distinction clear?
Vikram, just to clarify, so you're saying the second one can only be called from unsafe blocks. The
Yes.
first one you can call from any other place.
Yes.
And that makes it, of course, transparent to the user of, let's say, a library that this is unsafe. And maybe this is not a well-formed question or not relevant, but for the second option, are all three lines there now? Well, I guess if you're calling it from an unsafe block, they're all part of unsafe. So you can't have an unsafe block inside a function labeled unsafe.
I think you can technically put it, but it won't do anything. Like,
okay, yeah, it's like it just expands to the full function.
Yeah, exactly.
Perfect. Thank you.
So that is the essence of unsafety. And what this means is that if we encapsulate unsafety, you need to be very careful that you're doing it right. Otherwise, it transitively breaks everything down the chain. Any function that calls this in turn will be compromised, and any function that calls that too will be compromised, and so on. Right? So again, just to recap, if a function has encapsulated unsafe code, then it should behave like a safe function to its callers. And if a function doesn't encapsulate its unsafety correctly, then it transitively compromises the safety of every function that relies on it, even downstream, right? So that's the idea of encapsulating unsafe code. Now, once again, we go back to this like huge system of vulnerabilities that we had, and now it seems all the more ominous, right? We have these many different types of vulnerabilities, and even one of them in a crate means that the entire program is no longer safe. You could use a crate or a package that on the surface appears fine, but then there could be some hidden behavior inside it that causes it to seg fault, for example. Right? And here are some of these. Now let's look at some of these again, now that we know a few features of Rust. Here are some examples are like duplicate ownership can lead to double freeing. That is, value gets dropped twice, right? Incorrect bound checks while dereferencing raw pointers. Because when you dereference raw pointers, you need to make sure that the thing you're pointing to is valid, right? So incorrect bound checks. Transmuting from one type to another. There's a system to transmute. That is, with the same bytes, you change the way you change the type of those bytes. So for example, I can have a set of 8 bytes and look at it as an unsigned integer, or I can look at it as a character, for example, a set of characters. So then another example is where dereferencing allows mutable references to the same location. There's all sorts of these types of bugs. Incorrect lifetime bounds on return values. We're going to look at what this means soon. But the essence is that there are so many different types of memory safety errors. And what we would ideally like to do is have a system to potentially catch some of these during development or during compilation, right? We want to make sure that even if it's an over approximation, even if we potentially flag some valid programs as invalid, we still want to alert the developer that, hey, there's something weird going on here. Are you sure you know what you're doing, right? And that system would be sort of nice to have if you could do a quick like parse of a Rust package once we develop it, or just before it goes into production, just to check that these are all the potential errors and highlight various regions as being suspicious. And then someone can manually go through them and try to see whether they're actually implemented properly. Or the base case of doing this is, of course, just flag every unsafe block, like ask someone to go to every unsafe block and check that it's implemented correctly. But we want to be a little more specific than that, right? If there are 3,500 unsafe blocks in a program, then we can't ask someone to go to all of them. We want to say that, look, out of all these unsafe blocks, these 20 look like potentially suspicious, like there's something weird going on in them. Go and take a closer look at them. So with that in mind, we're going to try and come up with a system that is sort of an over approximation of what errors may occur in unsafe blocks, and we're okay with some false positives. Okay, so let's keep that in mind, and then going forward, let's try to develop a system that tries to catch some of these. So potentially, So in this particular case, what we're trying to do is focus on one particular type of memory error, and that is incorrect lifetime bounds and returned values. This is what we've looked at so far, and I'm going to be talking a little more about our work on detecting incorrect lifetime bounds. So before that, I should introduce the concept of a lifetime, because again, it's something unique to Rust and is not perhaps instantly intuitive when you look at it. Okay, so lifetime annotation bugs are what we're going to be looking at. Okay, what is a lifetime? A lifetime is a construct that the Rust borrow checker uses to ensure that all borrows are valid. So if you recall, a borrow is like a reference. When we do ampersand a or ampersand x, where the variable is x, we need to check whether that borrow is valid. And what Rust uses for that is something called lifetimes. And a fundamental rule is, it's similar to scope, right? Lifetime, it has some subtle differences from scope, but as a first approximation, it serves us well to think of it as scope. A borrow is valid if the lifetime of a borrow ends before the lifetime of a lender, right? So that is the thing you're pointing to must outlive the pointer itself. You cannot have a case where you have a pointer and the variable that points to is no longer alive. Then that could result in like a seg fault when you try to dereference the pointer, right? So that is the fundamental rule. Perhaps in this case, a better um, word would be like reference, must outlive the reference. Okay, so this is the concept of lifetimes, and then you're going to make this more clear with some examples. So in this case, the lifetime of x ends before the lifetime of r. So lifetime of x is this small block here. The lifetime of r is the bigger block here. So this will not compile, right? Because now the location r points to something which is no longer alive. X has now finished its lifetime and r is still alive. So this program will not even compile. Does that make sense?
Yeah, Vikram, I think there are no questions related to this. I think it does make sense. Yes.
Okay. So that is the concept of lifetimes. And now we're going to see how we can explicitly annotate lifetimes. So Rust can allow us to explicitly annotate identifiers with lifetimes like A, B, and foo, anything we want, basically, right? And it's indicated with this apostrophe over here, indicating that this denotes a lifetime parameter. Each lifetime parameter corresponds to a statically defined region of a program. So like a concrete scope, a concrete lifetime is a statically defined region in the program. At compile time, the compiler goes through the entire program and tries to assign these statically defined regions to each lifetime parameter. Right? One by one, it tries to say, okay, A maps to this region in the program, B maps to this region in the program, and so on. And the rule is that the variable can live for at most as long as the scope corresponding to the lifetime parameter. So if I annotate a variable with A, it means that the object that basically means that the variable A can itself live for at most as long as that scope. So that's the basic rule of lifetimes. And now this has an implication that if a variable can live for at most as long as A, then in practice, in most cases, if a reference has lifetime A, then the variable that it points to must live at least as long as A. So at most becomes at least when you're talking about the variable that's being pointed to. Okay, so that's that. Just to go over this again, a variable can live for at most as long as the scope corresponding to the lifetime parameter. But when that variable is a reference, then the thing that it points to must live at least as long as that A, in most cases, in practice. Right?
Yeah, that makes sense, Vikram.
Okay, so just to reiterate, in one case, we're talking about the lifetime of the variable. In one case, we're talking about the lifetime of the thing that it points to. And because of that, the at most gets flipped and becomes at least when we're talking about the thing that the thing that is being pointed to. Okay, so that's where we are on lifetimes. Now here is a simple example of lifetime annotations. We have a function that takes two arguments, x and y, with annotated with lifetimes a and a. and it returns a string also annotated with lifetime A. So these are all references, by the way, reference to string, reference to string, and reference to string. Now, what does this mean? This essentially says that the lifetime of the thing that X points to is at least A. The lifetime of the thing that Y points to is at least A. And likewise, the lifetime of the return thing is also at least A. Right? So Rust, in this case, if I did not provide lifetimes, would not know how long this returned object should live. Because this is like a dynamic construct, right? This is either X or Y. Does the return thing live as long as X, or does it live as long as Y? We don't know, right? There's no way for the Rust compiler to tell. What we do instead is say that each of these things must live at least as long as A. So if X lives for 10 lines in the code, Y lives for 5 lines, then A would correspond to the 5, and let's say that one is a subset of the other, right? Like Y is a subset of those 5 lines are a subset of those 10 lines. Then A would be the shorter of those 2 lifetimes, because you're talking about at least, right? And the return thing would also be the shorter of those 2 lifetimes. Does that make sense? We're talking about this can live at least as long as A. This also lives at least as long as A. So that essentially means that the shorter of the 2 lifetimes will be the lifetime A, which is also the lifetime of the returned object.
Yeah, that sounds good, Victor.
That's that's the notion of lifetime annotations on variables. Now, this is how it works in practice. But the problem here is that raw pointers don't have lifetime annotations. Rust doesn't track lifetime of objects that they point to, right? That is a sort of a problem, a fundamental problem when it comes to raw pointers. If it was a normal reference, I would know exactly uh, how long it would live and how long the object it pointed to would live, because I would annotate it with that lifetime parameter A. But raw pointers do not have lifetime annotations. So that potentially introduces bugs, and we define 3 types of bugs involving raw pointers. We're going to talk about those in the forthcoming slides. But the root of all these problems is the fact that raw pointers exist and raw pointers don't have annotated lifetimes. Okay, so 3 types of bugs. Let's go through them one by one. Now that we've understood like what it means for lifetimes to be annotated, and we have a rough idea of what it means to have these arguments to a function also annotated with lifetimes A, right? We say that the concrete lifetime assigned to this is the shorter of these 2, and so on. Let's look at 3 types of bugs. Okay, a lot happening in this slide. I'm going to try and break it down bit by bit. The first type of bug occurs when you have a raw pointer to age. So I have a structure with a raw pointer age, right, for example, and this does not have an annotated lifetime, as we can see, right? This age raw pointer does not have an annotated lifetime. And what I'm actually doing in this function is taking the self object, that is the pointer itself, and returning the value of the raw pointer. So I'm taking the self object, that's the structure, and returning the raw pointer. And unfortunately, since the raw pointer does not have an annotated lifetime, I have to assign a lifetime to the returned object. I have to say that this returned object has some lifetime B. If A and B are not the same, that is potentially problematic. Because now I'm saying that this returned object has some lifetime, but the self object borrow has a different lifetime. So it is entirely possible that this thing is now borrowed for a different scope than this thing is borrowed. Like I hear my unmuted, so I'm going to pause for a second. Are there any questions?
No, I think I don't see anything related to this. I mean, I think for anyone new to Rust, when you first start seeing lifetimes, it is pretty confusing because
I
one is
agree.
not
Yeah.
used to thinking in those terms. Um,
Mm.
But I think, yeah, the key point is what you just made, Vikram, which is the way this code is written right now. You have 2 different lifetime annotations. And so the compiler has the flexibility to assign you could think of it as two different scopes
Exactly.
to the return value and to the record object.
Yeah. Essentially, the record object is borrowed for a little while, and that little while is determined by A. And the returned object is also a reference, and that reference, the thing it points to, should be valid for B. So, what if we had a case where um, this returned object pointed to something that went out of scope, but then you could still access that thing through A, right?
Yeah,
The,
exactly.
the idea is that the lifetime B should be at least as long as the lifetime A. So this is one potential type of lifetime bug where which we've also seen in practice. Here is a real world example. I'm going to just leave this link here, and later, of course, the slides will be shared with everyone. So this link outlines a real world example of this kind of bug. So this is like a simplified, stripped down version of a real bug in Rust that um, is simply caused by incorrect lifetime annotation. If I had changed both of these to A, then the bug would disappear. Right? It's
So
as simple as that sometimes.
Vikram, sorry. So you answered this question, but there's a, basically the same question, which is this just an example to illustrate this kind of a bug, or are there practical use cases for specifying different lifetimes for the self object and the return value, where the return value is, so you have an object, you're returning a reference to an let's say a member of that object, and
Mm.
are there practical use cases where you want them to have different lifetimes? And I'm guessing your real world example basically is that example.
No, so actually, the real world example is perhaps incorrectly done. As in, I don't think there's any practical use case to having different lifetimes on the two objects. What that essentially does is it introduces potential for memory safety bugs and errors. I can't think of any case where you would want the. So it sort of goes against the principle that you should keep track of what you're borrowing, right? This basically allows you to borrow something without indicating that it's being borrowed. In some scope, it's possible that it's actually being borrowed, but the annotation tells it that it's not being borrowed. So that is not something which I think can have any practical use.
And
It
I
is
can maybe flip that around for Wanda's question, which is what you're basically saying is the compiler should not have this flexibility. In this particular case, when you have a reference to a member of of a struct,
exactly,
but the
exactly.
way it's defined as we can give this flexibility to the compiler, and we shouldn't be able to.
Exactly. So, for example, if this was not a raw pointer, right, if this was just a reference, then this would not be possible. I would have to annotate that reference itself with a lifetime A, and then that would reflect in the fact that you cannot assign a different lifetime to the thing that you're returning. Um, this only arises because the raw pointer doesn't have an associated lifetime, and that allows us this kind of flexibility. Um, the reason the Rust compiler doesn't flag it is because there are potentially valid programs that can also get rejected. It's sort of like an over approximation, right? Rust essentially does an over approximation at every stage. It says that um, uh, of course, yeah, the Rust compiler itself is an over approximation of valid programs. But when you now go to unsafe code, it wants to make absolutely sure that what it's flagging as incorrect is actually incorrect. So when you go into unsafe domains, it sort of becomes imprecise at the cost of allowing more flexibility. We are going to try and flip that around and say that even in the unsafe domain, we want to flag potentially incorrect code as incorrect. Right? We're going to say that even within unsafe, we want to impose some of the kinds of guarantees that Safe Rust gives us. And not impose as such, but more like suggest. Say, hey, there's something strange happening here. Just take a closer look and see if this actually works, right? Um, More like sort of being a recommendation tool, something that developers can lean on rather than something that is like a that produces compile errors. We don't want it to be like a later stage of the compiler. We want it to be more like a a final pass, if you will, like a quick recommendation check. Like, do you think that this is okay? That's the idea we're going for here, right?
Yeah, that makes a lot of sense.
Okay, so this is one type of bug, and the other two are going to be somewhat similar. We're just going to look at cases where you have raw pointers inside structures, and you have functions that either take these raw pointers as arguments or return these raw pointers. So we're going to look at one more case here. Here we are taking a reference to self, a reference to age, and we are assigning self.age equals age. So on the face of it, this might seem okay. We're saying, okay, this has lifetime A, this has lifetime A, so what's the problem, right? The problem is that this lifetime A is the lifetime of the borrow to self. It is not the lifetime of self itself. Self itself. But the idea is that the record structure, the structure object, has a different lifetime. That could be anything at all. The lifetime of the borrow to self is A, but the lifetime of self is something else. So it is possible that self.age now points to something, but that eventually sort of expires. Like self.age, the lifetime of this ends. The lifetime of this age object ends, and the thing that it's pointing to is no longer valid. But the structure itself is still around, and that can again potentially be problematic if you try to do things with that structure, and under the assumption that the raw pointer inside it is still invalid, is still valid. So here is a real world example once again. We again found this example while scanning our list of Rust sec vulnerabilities. And again, this is a simple example that could be fixed by proper lifetime annotation. So yeah, vulnerability type 2. Exhibit 3 is another case where we have like a constructor. We have a thing that returns a structure object with lifetime A, and it takes a reference with lifetime B. So the record is borrowing this reference object. So the thing inside it should live at least as long as the lifetime of the structure object. Again, you cannot have a case where the object now is still around, but the reference inside it is no longer valid. So we want to ensure that this lifetime A is not greater than this lifetime B. Okay, so that's what we want to ensure in this case. 3 types of bugs, just to recap. One is like a get method, one is like a set method, and one is like a constructor. In each of these 3 cases, we found real world examples where it actually happens, and they can all be simply solved by annotating the lifetimes correctly. In this case, all you have to do was remove this B and make them all A. Right? If we did that, then it would be simple. I know it seems like sort of quite facile on the surface of it, but when you're writing large programs involving like tens of files, each with hundreds of lines, it's very easy to write like one single function like this that just slips in an incorrect lifetime annotation, because it's very hard for programmers to reason about it. And at the root of it is the simple fact that if I annotated the lifetime correctly, I would be in safe territory, like entirely safe territory. But just because I'm not annotating lifetimes correctly, it introduces this potential vulnerability. So what we have here is something interesting. It's something very concrete. That is, it's just a simple annotation missing or an incorrect annotation. And it's something very problematic because the things it returns can potentially lead to vulnerabilities. And at the same time, it introduces potential for us to try and fix these bugs by coming up with an automated system. So that's exactly what we attempted to do in this particular case. We defined the simple algorithm as follows. Okay, an algorithm to detect lifetime bugs. That's my final part of the talk. Okay, we build on this framework called Rudra. This is a prior work to us that also tries to identify some certain memory safety bugs in the Rust ecosystem. So we sort of adapt their code and build on it to now introduce lifetime bug checking into their framework. And the outline is as follows. step A, find all structures with raw pointers, because these are what introduced the vulnerabilities in the first place. Find all functions where references to these are arguments or returned. That is, find functions like this, and like this, right? 3 types of functions, find all of them. Look for data flows to and from the raw pointers inside. So we want to actually make sure that, for example, we are taking this X inside the record, or that we're taking the age into the self object. We want to actually make sure that the values are going in, right? Look for data flows in. Check for type 1, type 2, and type 3 lifetime bugs. The 3 types that we defined, just exhaustively check all those cases, right? And that's the essence of our algorithm. Repeat this procedure for all structures with raw pointers, all functions where these structures are involved, and iterate through the 3 different types of lifetime bugs, and apply these rules verbatim. How it is, as I said, possible to have false positives with this approach, but that is acceptable. That's what we've been going for this whole time, that we're looking for something that provides actionable recommendations to the programmer or developer, but does not sort of restrict the developer from actually writing code. So we want to say that there is something potentially problematic in this code, but we don't want to actually like flag it as something that does not compile. Okay, so that's the idea. And so here is a simple toy program. We put all those 3 types of functions, and we also introduced like all the types of bugs that we've discussed so far. It has like every type of bug you can imagine with regards lifetimes. So our program successfully flags these 3. It says set age has a vulnerability, get age has a vulnerability, create has a vulnerability. And it also gives you exactly what the problem is. It says that the lifetime of the structure object containing a raw pointer is this, but it also takes a reference with a different lifetime this, and so on, right? It tells you exactly what the different lifetimes are and what the problem is and how to fix it. So that is good. That is something that is sort of a useful tool for someone writing a program to know, right? Like run this as a scan, and then it throws up these potential problems, and go through them and make sure that you've done everything right. And what we haven't shown here, okay, so future work, moving on. This is a work in progress. So we haven't, this output does not yet include data flow analysis, which is a key point, right? We need to actually make sure that the pointers are being transferred or that the value is actually pointing to that location. This is essentially step 1, step 2, and then step 4. The other factor is that we haven't shown you the different cases where it actually flags correct functions as incorrect. So that also happens, and that is all part of the process of reducing false positives. So that's another sort of future direction that we need to work on. And of course, eventually try to knock off these various categories one by one, try to sort of write rules that will flag potential violations of each of these different kinds of rules, transmuting from one type to another, incorrect bound checks, integer overflow, duplicate ownership, and so on. We want to sort of go through this entire hierarchy one by one and knock off these different types of bugs. So just to recap, we have a system that can take a program like this, give you output like this that tells you what different functions are potentially problematic and what is the error with them that we find. And it's still a work in progress because we have a few things we haven't implemented yet, and a lot of types of bugs that we haven't yet been able to catch. So that is where we stand. And I'm going to stop here and open the floor to any questions if anyone has any. I'm happy to take any questions and discuss anything that you find interesting. So thank you.
Thanks so much, Vikram. Thanks, Malhar. And if anyone has questions or you just want to even chat about this, you can join the stage, or as usual, write some questions in chat. So Vikram, we don't seem to have any more questions.
Okay. Do you have any questions you want to ask Sanjay? Did anything occur?
So that's perfect. So if there are no more questions, but if you do have questions later, please feel free to email any of us, and we'll be more than happy to talk about this. And let's thank Vikram and Malhan again for really good talks. And I don't know, Heidi, do you want to wrap this up with an announcement about the next research day? There she is.
Sure. My, what a great idea. So thanks everybody for attending. We are going to have another Research Day talk. We have these monthly. And I have lost the little slide that we had suggested. I can share it after I log off, but the next talk is going to be on June 30th. It is on bringing packet queuing to XDP, and it will be at 8 a.m. Eastern Standard Time. Our speaker is in the Czech Republic for that talk. So we'll put up a link, a slide after I leave, and hope to see you all there. Thank you very much. And thank you, Vikram, for taking us through all that detailed analysis and sparking a lot of debate in chat, even though we didn't get to see everybody's faces and voices. It was definitely very interesting and exciting talk.
Can I just also I'd also like to thank everyone for the excellent discussion in the chat. I'm just going through it now. I wasn't able to look at it during the presentation, but really fascinating points and excellent discussion. So I'd like to thank everyone who sort of chipped in, and I look forward to reading through this all in detail now that.
Great.
And I would like to thank Red Hat, the whole team, to generously sponsor this research and supporting Vikram in this way.
Yeah, likewise, thanks to everyone at Red Hat. Really enjoyed working with you all so far, and look forward to continuing working with you all. And also my advisor by Shaki for guiding me. Yes.
Perfect. Thanks, everyone.
Bye.
Bye.